Hello, everyone. Today, our group will be presenting our project called Data Optimization. My name is Nico, and I'll start by explaining the background and purpose of our project. We're going to move on to the slide where we can see the agenda of today, which we're going to talk about. So I'm going to move right into it. First slide, people all over the world face problems related to food and diet. Some have troubles eating the right balance of nutrition, while on the other side, some struggle to manage food costs. And because of that, our goal is to use optimization to find a diet that has both healthy and cost efficiency, something that meets nutritional needs without spending too much money. With that being said, on this slide, our project also connects to the United Nations Sustainable Development Goals. It supports goals like no poverty and zero hunger by helping people afford healthy food. On the other side, it also promotes good health and well-being by meeting basic nutrition needs and responsible consumption by reducing food waste. Overall, you can see that our goal is to make diet more affordable, healthy, and sustainable. Through this project, we show how optimization can help make diets more affordable, balanced, and sustainable. With that being said, I'm going to pass it to Nikki.
So our model uses 8 decision variables labeled X1 through X8, which represent each of the different food groups: meats, vegetables, fruit, legumes, starches, oils, nuts, and dairy. And the coefficients below represent the cost in US dollars per 100 grams of each food group. As we said before, the goal of the model is to minimize total cost, which you can see in our objective function. Next slide. To make sure that our model was realistic, we added multiple constraints, starting with that our overall diet must have at least 2,500 calories. And on top of that, we added a constraint for each nutrient category. Like you can see below, protein has to be between 50 and 200 grams, and carbs has to be between 130 and 300 grams. That being said, I'll pass it to Grant.
So here you can see our complete model, but we're mostly going to dive into the decision variable matrix here. So we got our cost from the Federal Reserve Bank for each decision variable per 100 grams. And then we also use the protein, carb, fat, sugar, and fiber values to then calculate all of our constraints in comparison to our decision variables. So I'll pass it to Jiwoon.
So here's our answer report. At the end of the day, the final value comes out to be $10.22 for one day. For each variable, for example, 508.95 grams of meat at $1.39 per 100 grams, and 152.65 grams of legumes at 34 cents per 100 grams, and so on. Next is a sensitivity analysis. This is a what if scenario. So what if meat coefficient changes from 1.39 to 2.00 and 1.39 to 0.50? So 2.0 is within the 2.5329, so we keep the solution, making the meat more expensive while minimizing the cost. The objective function value increases by 3.105. On the other hand, 0.5 is beyond the allowable decrease range of 0.6644, which makes the meat prices too low. So in this case, we would have to rerun the solver and find the new optimal solution. And I'll pass it on to Grant.
So here's our constraint sensitivity analysis. So for our binding constraints, anything with a shadow price, actively limit the solution by changing their limits, and that would impact the objective value. So for non-binding constraints, anything with a zero shadow price has slack, and adjusting it won't impact the optimal solution. For our shadow prices, though, the objective function changes if a constraint right-hand side changes by 1 unit. So for example, if we were to raise the max fiber constraint value from 25 grams to 30 grams, we would see an increase of 5 grams, and that would decrease our minimum cost objective solution by $0.128. So I'll pass it on.
Okay, so what are the real world applications of this model? Well, government and nonprofits can take this model to plan things like school lunches, hospital meal plans, and importantly, humanitarian aid packages. In response to a crisis, distributing good food can be a nightmare in terms of cost. So by using optimization models, the best combination of foods that meet calorie and nutritional needs, as well as staying within budget, can be found. This ensures limited resources feed as many people as possible without sacrificing nutritional quality, which is a crucial factor in emergencies and long-term situations. Next slide, please. So in conclusion, our model shows how linear programming can solve practical everyday problems as well as large-scale humanitarian efforts. By setting clear objectives and constraints, we can use data and computation to make smarter, more efficient decisions for the betterment of all. Thank you.